Everything you know about the cosmos might be a beautiful lie. We are about to embark on a journey through 30 cosmic truths so strange they seem ripped from science fiction, each one challenging the very foundations of what science has taught us. You will discover a hidden reality where time is flexible, empty space holds the key to everything, and the universe itself might be a grand illusion. By the end of this, your perception of reality will be fundamentally altered. We will uncover why black holes are nothing like you imagine and how the fabric of space could one day tear everything apart. What part of the universe's story are you most excited to have rewritten? Our universe is not expanding from a single point like an explosion in an empty void. The Big Bang happened everywhere at once. Think of the entire cosmos as the surface of an inflating balloon with galaxies painted on it like tiny dots. As you blow air into the balloon, every single dot moves away from every other dot. Not a single one of those galaxies is at the center of that expanding surface. The center of that balloon is not a part of the surface at all. It is a separate dimension we cannot access. This is the reality of our universe. We are not rushing away from the site of some primeval cataclysm. We are embedded within the stretching fabric of space-time itself. Every point in the cosmos is, from its own perspective, the center of the expansion. This truth shatters the deeply human instinct that we occupy a special, central place. We are on just one of those dots, looking out at a cosmos where every direction appears to be moving away, not because we are at the center of everything, but because everything is everywhere all at once. This realization fundamentally redefines our cosmic address from a privileged spot to a humble neighborhood in an infinite metropolis. This invisible scaffold holds our entire universe together. We call it dark matter, a substance so ghostly it refuses to interact with light in any way. You are currently breathing it, your body is passing through its unseen particles, yet you feel absolutely nothing. It is the cosmic ghost in the machine, and it is 5 times more abundant than all the atoms that make up every star, planet, and person you have ever seen. Its existence is not just a theory, it is a gravitational certainty. We watch galaxies spin at speeds that should tear them apart, flinging stars into the void. Yet they remain intact, held together by the immense, unseen gravity of a dark matter halo that envelops them. The very fact that our own galaxy exists in its current form is proof that we are swimming in an ocean of something we cannot see. For decades, scientists have built exquisitely sensitive detectors deep underground, shielded from cosmic rays, hoping for a single, fleeting interaction. So far, the silence is profound. Whatever dark matter is, it is not just dark, it is profoundly, bafflingly shy. It shapes the cosmos on the grandest scales, dictating the fate of galaxies, yet it remains the universe's greatest secret, a reminder that most of reality is fundamentally hidden from our senses. That ghostly dark matter is not the only emptiness defining our reality. If you could remove all the empty space from every atom in your body, the entire human race would fit into a volume smaller than a sugar cube. This is the staggering truth of our material world. An atom is a cathedral of nothingness. Picture its nucleus, a tiny dense core of protons and neutrons, as a single fly buzzing in the middle of a vast sports stadium. The electrons whizzing around the outermost seats are nothing more than distant, shimmering dust motes. Everything in between, the immense volume of the arena, is pure, unadulterated vacuum. The solidity you feel when you touch a table or the ground is an illusion created by electromagnetic forces, a persistent repulsion between the outer shells of these mostly hollow structures. You are not actually touching anything, you are just feeling a field of energy pushing back. Now, take this concept of profound emptiness and scale it up to the cosmos. The distances between stars make atomic emptiness seem cluttered by comparison. The void between our Sun and its nearest neighbor, Alpha Centauri, is so immense that every event in recorded human history, from the construction of the pyramids to the invention of the internet, could unfold within the time it takes a beam of light to cross that chasm. All our wars, our art, our love stories, and our discoveries are just a fleeting whisper in the cosmic silence between two insignificant stellar neighbors. This is the universe's true nature, an overwhelming expanse of nothing, punctuated by rare, isolated islands of something. The profound emptiness between stars is matched only by another cosmic illusion, the steady and universal ticking of time. Time itself is not a rigid river flowing at the same speed for everyone. It is a flexible, personal experience warped by gravity and motion. A clock attached to a GPS satellite in orbit, high above the Earth where our planet's gravity is weaker, actually runs faster than an identical clock on the ground. If engineers did not constantly correct for this tiny difference, the entire global positioning system would become useless within a single day, its navigation errors accumulating by several miles. This is not a theoretical idea, it is a daily, practical application of Einstein's theory of relativity. Even an astronaut on the International Space Station, racing around the planet at thousands of miles per hour, experiences time slightly slower than we do. Over a long mission, they return to Earth having aged a tiny fraction of a second less than everyone they left behind. They have, in a very real sense, traveled a minuscule amount into the future. This means your head is actually aging faster than your feet because it is ever so slightly farther from Earth's gravitational pull. The time you experience sitting still is different from the time experienced by someone flying in a jet, and different again from a particle racing at near light speed. There is no single now that blankets the cosmos. The universe operates on a tapestry of individual times, each thread stretched and compressed by where it is and how fast it is moving. Even the ultimate speed limit, the velocity of light, can be broken by the cosmos itself. Distant galaxies are receding from us at speeds greater than light, a fact that seems to shatter Einstein's most famous rule. But the rule remains unbroken because those galaxies are not moving through space, they are being carried away by the stretching of space itself. Picture a loaf of raisin bread rising in the oven. The dough, representing space itself, is expanding. Two raisins that start close together move apart slowly, but two raisins that are far apart, separated by more stretching dough, move away from each other much faster. For raisins on opposite ends of the loaf, the dough between them is stretching so fast that their separation speed surpasses that of any single raisin moving through the dough. This is the reality of our universe. The fabric of space-time is stretching, and for galaxies beyond a certain cosmic horizon, the cumulative stretching between us and them adds up to a velocity we can never hope to match. This has a profound and lonely consequence. The light from those superfast galaxies is fighting a losing battle against the expansion. It is like a swimmer trying to cross a river that is widening faster than they can swim. The photons are stretched into longer, redder wavelengths, their energy sapped by the journey until one day they will simply never reach us. Most of the galaxies we see today will eventually be carried beyond our cosmic horizon, their light fading to nothing. The universe of the far future will be a much darker, emptier place, with our local group of galaxies isolated in an ocean of expanding blackness, the evidence of a grander cosmos forever erased from the sky. This strange stretching of space is not the only rule that gets broken on the cosmic stage. Down in the subatomic realm, particles engage in a connection so bizarre it seems to mock the very idea of distance. Two particles can become linked or entangled, sharing a single existence no matter how far apart they are separated. If you measure a property of one, like its spin, you instantly know the spin of its partner, even if that partner is on the other side of the galaxy. This is not a matter of sending a signal. The information seems to be communicated in zero time, a phenomenon Einstein himself called spooky action at a distance. It is as if you had a pair of magical coins. You flip one coin in New York and it lands on heads, and you know without any delay that its entangled twin in Tokyo has simultaneously landed on tails. This connection appears to violate the cosmic speed limit of light and our deepest intuition about cause and effect. How can something here influence something there without any time for a message to travel? The answer is not that information is traveling faster than light, but that the two particles do not have separate identities to begin with. They are part of a single, unified quantum system. Measuring one particle does not send a message to the other. It simply reveals the shared state that always existed between them. This forces us to confront a radical idea that the universe at its most fundamental level may not be made of separate, isolated things, but is instead a deeply interconnected web where the concepts of here and there are not as absolute as they feel. This profound interconnectedness hints at a universe far richer than we can perceive, and its sheer scale is almost impossible to grasp. The number of stars in the observable universe is greater than all the grains of sand on every beach and in every desert on our entire planet. Every single time you have stood on a shoreline looking out at a seemingly infinite stretch of sand, you were holding a mere handful in a cosmic ocean. The mathematics behind this is staggering. Scientists estimate our planet holds roughly 7 quintillion, 500 quadrillion grains of sand. That is a 7 followed by 18 zeros. An unimaginable number, yet the observable universe contains around 1 septillion stars. That is a 1 followed by 24 zeros. For every single grain of sand you could ever hold, there are thousands upon thousands of suns shining in the void. Each of those stars is a potential sun, many with their own families of planets. This astronomical abundance makes one conclusion feel almost inevitable. Life must exist elsewhere. The raw ingredients for life, the carbon, oxygen, and nitrogen forged in stellar furnaces, are scattered throughout the galaxy. With so many worlds orbiting within the habitable zones of their stars, where temperatures allow for liquid water, the probability that biology has sparked on at least one other world seems overwhelming. The universe has had over 13 billion years to experiment, to mix and match these ingredients on an incalculable number of planetary canvases. The silence we hear when we listen for alien signals is not a sign of emptiness. It is a testament to the vast, lonely distances between islands of life and the fleeting nature of civilizations against the cosmic clock. We are almost certainly not alone, but we may be forever separated by a gulf not just of space but of time. A black hole's gravity is no more powerful than that of a star with the same mass. If our sun were instantly compressed into a black hole, something impossible in reality, Earth and all the planets would continue to orbit precisely as they do now. They would simply be circling an absolute darkness. The terrifying pull we associate with these objects only becomes inescapable once you cross a specific threshold, the event horizon. This is not a physical surface you could touch, but a point of no return in space, a one-way door from which not even light can escape. Far from this boundary, a black hole's gravity behaves just like the gravity of any other object. The danger is not that they suck everything in, but that they offer no second chances to whatever falls through their door. We are all living proof of this stability. Every star you see in the night sky, including our own sun, is gracefully orbiting the supermassive black hole at the heart of the Milky Way. We call this colossal object Sagittarius a star. It possesses the mass of 4 million suns, yet it holds our entire galaxy in a gentle gravitational dance from 26,000 light-years away. Its influence is vast but subtle, a cosmic anchor around which our galactic home slowly turns. This reveals a profound truth about the universe, that the most destructive forces are often the same ones that provide the structure for existence itself. Even the coldest, darkest void of space is not truly cold. It holds a faint, universal warmth, a ghostly echo of the universe's fiery birth. This is the cosmic microwave background, and its temperature is a steady 2.7 degrees above absolute zero. That is just 2.7 degrees Celsius above the coldest temperature possible, where all atomic motion ceases. This afterglow fills every cubic centimeter of the universe, a relic from a time when the cosmos was a searing, opaque plasma. For the first 380,000 years of its existence, the universe was too hot and dense for atoms to form. Light particles, photons, were trapped in a constant, scrambling dance with free electrons, unable to travel in a straight line. The universe was a brilliant, blinding fog. Then, as expansion cooled everything, a monumental transition occurred. Electrons finally combined with nuclei to form the first stable atoms. In that instant, the fog lifted. The photons, once imprisoned, were suddenly set free on a journey across the cosmos. The light that was released in that single, universal moment is what we detect today as this microwave whisper. When you tune an old analog television to a dead channel, about 1% of the static snow you see is this primordial signal, the literal afterglow of creation arriving at your antenna from 13.8 billion years in the past. It is the oldest fossil we will ever have, a baby picture of the entire cosmos, and it tells us that the empty space around us is not empty at all. It is saturated with the faded energy of the beginning of everything. That faint cosmic whisper is a direct link to our own deepest origins. Every single atom in your body, from the oxygen in your lungs to the iron in your blood, was forged in the heart of a long-dead star. The universe began with only the two simplest elements, hydrogen and helium, scattered like cosmic confetti from the Big Bang. For millions of years, that was all that existed. Then gravity went to work, pulling these primordial clouds together until they ignited into the first generation of stars. Inside those stellar furnaces, a miracle of nuclear fusion began. Under unimaginable pressure and heat, hydrogen atoms were smashed together to form helium. As the star aged, helium fused into carbon and carbon into oxygen. Step by step, the periodic table was being written in the cores of stars. Your very carbon backbone, the fundamental structure of your DNA, was created in this way. But the story does not end there. For the heaviest elements, like the iron that carries oxygen through your veins, a more violent birth was required. A massive star, after spending millions of years patiently building elements layer by layer like a cosmic onion, ends its life in a cataclysmic supernova explosion. In that fleeting, brilliant flash, temperatures and pressures soar beyond comprehension, forging all the heavier atoms in an instant. The gold in a wedding ring, the iodine essential for your thyroid, the calcium in your bones, all were seeded into the cosmos by these stellar detonations. That expanding cloud of stardust, enriched with the elements for planets and life, eventually coalesced into new solar systems. Our sun is a second or third generation star formed from the ashes of its ancestors. The Earth and everyone on it is literally made from that recycled stardust. You are not just living in the universe is living in you. You are a way for the cosmos to know itself, a collection of ancient atoms that have journeyed for billions of years to come together for a moment as you. Our cosmic companion is slowly leaving us. The moon is drifting away from Earth at a rate of about 1.5 inches every single year. This gradual retreat is a direct result of the gravitational dance between our planet and its satellite, a phenomenon driven by tides. The moon's gravity pulls on Earth's oceans, creating the familiar bulge of high tide. But Earth's rotation is so fast that it actually drags this watery bulge slightly ahead of the point directly under the moon. This offset bulge then exerts its own gravitational pull on the moon, giving it a tiny push that boosts its orbit, forcing it ever so slowly outward. This process acts as a cosmic brake on our own world. The energy lost by Earth as it tugs on the moon is slowing down our planet's rotation, making our days longer. Billions of years ago, a day on Earth was only about 18 hours long. and the moon loomed much larger and closer in the sky. The dramatic ballet of a total solar eclipse was a far more common event, with the moon's larger apparent size completely smothering the sun's disk. In the unimaginably distant future, this will change. As the moon continues to recede, it will appear smaller and smaller in our sky. There will come a final, perfect total solar eclipse, after which the moon will never fully cover the sun again. The tides we rely on to mix the oceans and stabilize our climate will weaken significantly, becoming a mere shadow of their current strength. The constant, gentle breaking of our rotation will continue, stretching our days longer and longer, fundamentally altering the rhythms that have governed life on Earth for eons. That ancient starlight connecting us to the cosmos is also a message from the past. Every time you look up at the sun, you are not seeing it as it is now, but as it was 8 minutes ago. This is the time it takes for light to travel the 93 million miles from its surface to your eyes. If the sun were to suddenly vanish, a philosophical question that haunts many a physicist, we on Earth would enjoy 8 final minutes of ignorant sunshine before the sky went dark and its gravitational hold was released. This principle extends across the entire universe, transforming every telescope into a powerful time machine. When you gaze at the bright star Sirius on a clear night, you are witnessing light that left its surface 8 years ago. The light from the Andromeda Galaxy, the nearest major spiral to our own, is 2.5 million years old. We see it as it was when early hominids were first walking the plains of Africa. The most powerful observatories peer even further back, capturing the faint glow of galaxies so distant their light has been traveling for over 13 billion years. We see them not as the majestic, mature galaxies they may be today, but as they were in their cosmic infancy, mere toddlers in a young universe. This creates a unique historical record written in photons. By looking out into space, we are literally looking back in time, observing different epochs of cosmic evolution simultaneously. The night sky is not a flat painting, but a deep, layered archive. The star next to a distant galaxy in your telescope's viewfinder might be a relative newcomer, while the galaxy itself is an ancient relic. Our view of the cosmos is a chaotic collage of different moments, a single snapshot containing the fresh, the old, and the impossibly ancient, all presented together as if they were happening in the same now. This means we can never see the universe as it truly is, only as it once was. The idea that our reality is a grand projection sounds like science fiction, yet it is a serious possibility explored by physicists. This is the holographic principle, a theory proposing that our seemingly solid, three-dimensional universe might be nothing more than a hologram, an incredibly detailed illusion projected from information stored on a two-dimensional surface at the edge of everything we know. Think of the security hologram on your credit card. It appears to have depth and volume, a three-dimensional image you can almost touch. But that entire image is encoded on a flat, two-dimensional piece of plastic. The holographic principle suggests our entire cosmos operates in a similar way. The information describing every star, every planet, and every one of us could be perfectly encoded on a distant, spherical boundary that surrounds the observable universe. In this radical view, the three dimensions we experience are not fundamental. They emerge from a more basic, two-dimensional reality, much like the characters and landscapes in a movie emerge from the flat, two-dimensional data on a screen. The solidity you feel, the vast distances between galaxies, the very sense of depth itself, could all be a magnificent cosmic mirage. This principle was first discovered through the study of black holes, where physicists found that all the information describing what falls into a black hole is somehow encoded on its two-dimensional event horizon, the point of no return. The universe itself might be obeying the same rule on the grandest possible scale. Scientists are now searching for evidence in the faint whisper of the cosmic microwave background, looking for a specific kind of noise or graininess that would reveal the pixelated nature of spacetime. If confirmed, it would mean that the universe is not just expanding and evolving, but that it is literally rendered into existence, a breathtakingly complex projection from the ultimate screen at the edge of reality. Our universe may be just one page in an infinite cosmic library. The idea of a multiverse is not a single theory, but a consequence of several of our most successful scientific models. The first and perhaps most compelling version comes from the theory of cosmic inflation. This suggests that the rapid expansion of the early universe never truly stopped. Instead, the fabric of space-time is undergoing an eternal, bubbling expansion. Think of a vast, endlessly boiling pot of water. Our entire observable universe is just a single bubble that formed in this cosmic foam, one where the laws of physics settled into a configuration that allows for stars, planets, and us. But in this eternal froth, countless other bubbles are constantly nucleating, each one a separate universe with its own unique set of physical constants. In some, gravity might be repulsive, atoms could never form, or the strength of the nuclear force might lead to instant collapse. We do not live in a special bubble, just a stable one that permits our existence. This is the Level 1 multiverse, an endless array of disconnected cosmic domains forever beyond our reach. Another startling possibility comes from string theory with its concept of brane worlds. In this view, our entire three-dimensional universe could be a mere membrane or brane, floating within a higher dimensional space. Other branes, other entire universes, could be drifting mere millimeters away from us in an unseen dimension. We are like pages in a book, separated by an infinitesimal gap we cannot perceive or cross. A collision between two such branes could even have been the trigger for our own Big Bang, a shattering event echoing from a dimension we cannot access. Then there is the quantum multiverse, born from the many worlds interpretation. Every time a quantum event has multiple possible outcomes, the entire universe splits to accommodate each one. Did that radioactive atom decay or not? In one branch of reality, it did. In another, it did not. This is not just about atoms. Every choice, every chance event spawns new, fully real universes. In one world, you are listening to this script. In another, you never clicked play. These are not mere possibilities, but actualized realities, diverging endlessly in an ever-branching tree of existence. While we cannot visit these parallel worlds, their mathematical possibility forces us to ask a profound question. Is our universe a unique, finely tuned miracle, or are we simply one ordinary reality in an infinite ensemble where every possible law and history must somewhere be real? The profound silence between those branching universes is an illusion we impose on the cosmos. Space itself is not a silent movie, but a symphony playing on instruments we cannot hear with our naked ears. The vacuum may not carry sound waves like air does, but it is filled with pressure waves and electromagnetic vibrations that we can translate into sound. Scientists have taken the data from our most powerful telescopes and probes, shifting these inaudible frequencies into the range of human hearing, and the results are a haunting cosmic chorus. The magnetosphere of Jupiter, a colossal magnetic bubble surrounding the giant planet, crackles with intense radio emissions. When converted, it sounds like a roaring, churning sea of static, a testament to the immense forces at play. The solar wind, a constant stream of charged particles flowing from the sun, creates a persistent hiss as it washes over our own planet's magnetic field. But the most profound sounds come from the most destructive places. The supermassive black hole at the center of the Perseus galaxy cluster sends out pressure waves through the superheated gas that surrounds it, ripples that travel for hundreds of thousands of light years. Astronomers have extracted this sound, a single note played on the largest instrument imaginable. It is a B-flat, but a B-flat 57 octaves below middle C. This single note has been ringing out for over 2 billion years, its wavelength so vast that it would take a wave of sound 20 million years to complete a single oscillation. Listening to these translated sounds is like hearing the universe breathe. It is a reminder that the cosmos is not a still and passive void, but a dynamic, vibrating entity, constantly humming with the low, deep music of its own existence, a symphony of creation and destruction playing on an infinite loop. Our planet's own magnetic heartbeat is far from steady. Deep within Earth's core, a churning sea of molten iron generates a protective magnetic field that blankets our world, but this field is prone to dramatic and unpredictable reversals. The north and south magnetic poles have swapped places hundreds of times throughout our planet's deep history, and the evidence for this is literally set in stone. When volcanic rock erupts and cools, tiny magnetic minerals within it lock in the direction of Earth's magnetic field at that exact moment, like a cosmic compass frozen in time. By studying these ancient lava flows across the globe, scientists have constructed a timeline of these flips, revealing that they occur at random intervals, sometimes hundreds of thousands of years apart. We are living on borrowed time, as the last full reversal happened nearly 800,000 years ago. Right now, the magnetic field is behaving strangely. It is weakening at an accelerating rate, with a particularly dramatic weak spot known as the South Atlantic anomaly already allowing more intense solar radiation to affect satellites and spacecraft that pass through it. This global weakening is a classic precursor to a pole reversal, a process that would not be a sudden switch but a long, chaotic transition that could span 1,000 years or more. During this time, the magnetic field would not vanish entirely, but it would become a complex, multipolar mess with multiple north and south poles popping up across the globe. This would be a period of immense vulnerability for our technology-driven civilization. Our planetary shield against solar and cosmic radiation would be critically compromised. Satellites in orbit, which rely on the magnetic field for protection, could be fried by solar storms, crippling global communications, GPS, and weather forecasting. Power grids on the surface could be subjected to devastating geomagnetic-induced currents, leading to widespread and prolonged blackouts. For life itself, the consequences are less clear. Migratory animals like birds, sea turtles, and whales that use the magnetic field for navigation would face immense confusion, potentially disrupting entire ecosystems. While there is no evidence that past reversals caused mass extinctions, they occurred in a world without a fragile technological web supporting 8 billion people. A pole reversal would not be an apocalyptic event for biology, but it would be a protracted crisis for our modern way of life, a slow-motion test of our resilience against the restless dynamo at the heart of our world. Our own galaxy is racing through the cosmos at over 1 million miles per hour, pulled by a force we cannot see. This mysterious destination is known as the Great Attractor, a gravitational anomaly so powerful it is drawing our entire Milky Way and thousands of neighboring galaxies toward a specific point in the constellation Centaurus. The problem is, we cannot look directly at it. Our view is completely blocked by the dense, dusty plane of our own galaxy, a cosmic blind spot that obscures nearly a quarter of the visible universe from our perspective. It is like trying to see a magnificent city on the other side of a towering, impenetrable mountain range. For decades, this region was one of the greatest puzzles in astronomy, a colossal something exerting its pull from behind a curtain of stars and interstellar dust. What could possibly possess enough mass to command the motion of so many galaxies? Early observations suggested a massive concentration of galaxies, a supercluster, was responsible. But as our measurements improved, it became clear that the Great Attractor was not the final destination, but merely a waypoint on a much larger, more terrifying journey. The true source of this cosmic river is something far grander and more distant, an entity we now call the Shapley Attractor, the most massive concentration of matter in our observable universe. Yet even this does not fully explain the local pull. The Great Attractor appears to be a dense knot in the cosmic web, a place where the filaments of dark matter and galaxies intersect, creating a gravitational well of immense proportions. We are like ants on a leaf, caught in a current we can measure, but whose ultimate source we are still struggling to see. New telescopes that can peer through the galactic dust using infrared and X-ray vision are slowly mapping this hidden realm, revealing clusters of galaxies and vast structures previously unknown. The mystery of the Great Attractor is a humbling reminder that we are not still, but passengers on a galactic voyage, hurtling toward a hidden center of gravity in a universe where most of the action remains quite literally behind the scenes. This relentless cosmic motion occurs within a framework we take for granted, the steady flow of time. Yet some of our most profound physical theories hint that time itself is not a fundamental part of the universe. It may be an emergent property, an illusion that bubbles up from the interactions of countless tiny quantum parts, much like the temperature of a gas emerges from the frantic motion of its individual molecules. At the deepest level, the equations governing the quantum world are often symmetric, working just as well backward as they do forward. There is no inherent arrow of time in the core laws of physics. The relentless forward march we experience so viscerally is nowhere to be found in these foundational rules. So where does our one-way journey from past to future come from? The answer may lie in a concept called entropy, which is essentially a measure of disorder. The universe as a whole has been progressing from a state of incredibly low entropy, a highly ordered and uniform beginning just after the Big Bang, toward a state of ever-increasing disorder and randomness. We perceive this grand cosmic smoothing out as the flow of time. It is the reason you can remember the past but not the future, why an egg scrambles easily but never unscrambles itself. Your own consciousness, your sense of a moment called now, might be a side effect of this universal progression from order to chaos. If time is not fundamental, then the past, present, and future might all exist simultaneously in a static, timeless block. The feeling of moving through time could be akin to a needle reading data from a DVD, experiencing the story one frame at a time, even though the entire movie is already there, complete and unchanging. This challenges the very core of our existence. What does free will mean if the future is already written? What is the present moment if it is just an arbitrary point in a frozen tapestry? We are left grappling with a universe that may be fundamentally timeless, where our most personal and persistent experience is nothing more than a magnificent, persistent ghost in the cosmic machine. The smooth, uniform glow of the cosmic microwave background was a lie. Our universe is not a homogeneous soup, but a vast, lumpy web of unimaginable scale. That primordial whisper of heat from the Big Bang contains the faintest of imprints, tiny ripples of density that were the cosmic seeds for everything we see today. In the earliest moments, quantum fluctuations, tiny hiccups in the fabric of reality itself, were stretched to enormous sizes during the period of inflation. These minute variations in density meant that some regions of the young universe had just a little more matter than others. Gravity is an amplifier of inequality. Over billions of years, it relentlessly pulled matter toward these slightly denser spots. The dark matter, which we cannot see, formed an invisible scaffold first, its gravity drawing in the ordinary atoms. What began as microscopic ripples grew into a colossal cosmic architecture, a sponge-like structure of staggering proportions. We now call this the cosmic web, and its map reveals a universe organized on the grandest of scales. Enormous, nearly empty voids, hundreds of millions of light-years across, are bordered by long, winding filaments of galaxies. Where these filaments intersect, they form dense knots, the great superclusters, each one a metropolis of thousands of galaxies. Our own Milky Way resides on the outskirts of the Laniakea supercluster, a gravitational collection of over 100,000 galaxies, all flowing toward the same hidden center of gravity. This lumpiness is the ultimate signature of our universe's history, a fossil record written in galaxies and emptiness. It tells us that the initial conditions of the cosmos were not perfectly smooth, and that the relentless pull of gravity, working on both the dark and the light, has been sculpting this magnificent, uneven tapestry for almost 14 billion years. That cosmic web, a tapestry of galaxies and immense voids, is itself built from a profound mystery. Everything you can see with your most powerful telescope, every star in every galaxy, every swirling nebula and wandering planet, accounts for a mere 5% of the entire universe. The atoms that form you, the Earth, and all visible cosmic structures are just the visible frosting on a cake whose main ingredients are completely invisible and unknown. The remaining 95% of the cosmos is composed of two shadowy components, dark matter and dark energy, and we have no idea what they truly are. Think of the entire universe as a grand $100 bill. The part we know and understand, all the ordinary matter made of protons, neutrons, and electrons, is a single $5 bill. The rest, $95, is divided into two forms of cosmic currency we cannot spend or even hold. Roughly $27 of that is dark matter, the invisible glue holding galaxies together. The remaining $68, the majority share of the cosmic budget, is the most mysterious of all, dark energy, the force relentlessly accelerating the expansion of the cosmos. This means that for thousands of years, our entire study of the heavens, from ancient astronomers charting constellations to modern scientists analyzing starlight, has been focused on a tiny, insignificant sliver of what is actually out there. We have been meticulously studying the foam on the surface of a vast, dark ocean, completely unaware of the immense, hidden depths beneath. Our reality, everything we can touch and see, is the exception, not the rule. The universe is primarily made of stuff that is fundamentally alien to our senses, a silent, dominant majority that governs the fate of everything, while our familiar world of atoms is just along for the ride. Our own sun is a cosmic middle child, a stable and reliable star currently in the very prime of its life. Classified as a G-type main sequence star, it has been fusing hydrogen into helium in its core for roughly 4.5 billion years, and it has another 5 billion years of fuel left. This places us at a quiet, comfortable midpoint in our star's life story, a period of remarkable stability that has allowed life on Earth to flourish. But this stability is temporary. In about 5 billion years, the sun will begin its slow, dramatic death. As it exhausts the hydrogen in its core, the delicate balance between the outward push of fusion and the inward crush of gravity will falter. The core will contract and heat up while the sun's outer layers will expand tremendously, swelling to engulf the inner planets. Mercury will be vaporized. Venus will follow, and Earth, our precious blue marble, will find itself orbiting inside the sun's outer atmosphere, its surface scorched into a molten ball of rock, its atmosphere stripped away by the stellar winds of a dying star. The sun will have become a red giant, a bloated, brilliant beacon in the solar system, its diameter stretching out nearly to our own orbit. This is the inevitable fate of our world, a final curtain written into the fundamental physics of our star. After its red giant phase, the sun will not go out with a bang. It will lack the mass for a supernova. Instead, it will gently shrug off its outer layers, creating a beautiful, glowing shell of gas called a planetary nebula. For a brief cosmic moment, this nebula will glow with intricate and brilliant colors, a final memorial to the star that once was. All that will remain is the sun's incredibly dense, Earth-sized core, a white dwarf star. This stellar ember will be fantastically hot, but with no new fusion to keep it burning, it will slowly, over trillions of years, cool and fade to a cold, black cinder in the void. This timeline is not just an astronomical curiosity, it is the ultimate clock for humanity's future. Our entire biological and technological destiny is tethered to the remaining lifetime of our star. It forces a profound perspective. 5 billion years is an almost incomprehensible span of time, 100 times longer than all of complex life on Earth. It offers an unimaginable runway for evolution, for exploration, and for the ultimate survival of our lineage, whether on this planet or scattered among the stars. The death of our sun is a certainty, but it is also a distant horizon, a reminder that our story as a species and a planet is likely still in its very first chapters. Our star is not a placid, constant light. It is a seething ball of plasma with a temper, and its outbursts can reach across 93 million miles to touch our world. This is space weather, a river of high-energy particles and radiation that constantly flows from the sun. Most of the time, our planet's magnetic field acts as a perfect shield, deflecting this solar wind and protecting us. But when the sun erupts, that shield can be overwhelmed. The most dramatic events are solar flares, intense flashes of radiation that can disrupt radio communications across the entire sunlit side of Earth in a matter of minutes. Even more powerful are coronal mass ejections, colossal bubbles of magnetized plasma hurled from the sun's outer atmosphere. These billion-ton clouds of charged particles race through the solar system at millions of miles per hour. When one is aimed directly at Earth, the consequences can be profound. We have a stark historical example of what can happen. In September 1859, a massive coronal mass ejection, now known as the Carrington event, slammed into our planet. The resulting geomagnetic storm was so intense that telegraph systems, the advanced technology of the era, failed worldwide. Operators received severe electric shocks, telegraph paper caught fire, and the aurora borealis was seen as far south as the Caribbean. The sky itself seemed to be on fire. If an event of that magnitude occurred today, the impact would be catastrophic. Our entire technological civilization is now built on a fragile electrical grid. A Carrington-level storm would induce powerful electrical currents in those long-distance power lines, frying transformers and causing a cascade of blackouts that could last for months or even years. It would be a silent, invisible collapse. Without power, water treatment plants would stop, refrigeration would fail, fuel pumps would be inoperable, and global communication networks would vanish. Satellites that govern our GPS, banking, and communications would be blinded or destroyed by the radiation blast. We got a small taste of this in March 1989, when a much smaller geomagnetic storm caused a 9-hour blackout across the entire province of Quebec, Canada. That event was a mere whisper compared to the roar of 1859. Scientists now monitor the sun constantly, giving us a precious day or two of warning, but our infrastructure remains dangerously vulnerable. This is a reminder that our place in the cosmos is not just a matter of astronomy, but of survival. The gentle sunlight that warms your skin is a placid mask for a star capable of unleashing a firestorm that could send our modern world back to the steam age. The very laws of physics we rely on to make sense of the cosmos might not be universal laws at all. For centuries, science has operated on a fundamental assumption that the rules governing reality are the same everywhere and for all time. The force of gravity, the speed of light, and the strength of the interactions between particles are believed to be constant, fixed numbers that hold true from your backyard to the farthest galaxy. This principle of uniformity is the bedrock of cosmology, allowing us to interpret the light from quasars billions of light years away with confidence. But what if that bedrock is cracking? A series of startling observations, primarily focused on the light from incredibly distant quasars, suggests that one of physics' most cherished constants might actually be inconstant. This is the fine structure constant, often represented by the Greek letter alpha. It is a pure number that governs the strength of the electromagnetic force, dictating how tightly atoms hold onto their electrons and how stars burn. If this number were even slightly different, the universe would be unrecognizable. Carbon-based life would be impossible, and chemistry as we know it would not exist. For decades, we measured alpha here on Earth and assumed it was the same across the cosmos. But when astronomers analyzed the absorption lines in the light from quasars, which act as cosmic fingerprints for distant clouds of gas, they found something perplexing. The patterns of these lines suggested that the value of alpha in those ancient regions of space was subtly different. In one direction of the sky, the data hinted it might have been weaker in the past, while in another direction it might have been stronger. This would mean that the electromagnetic force, and thus the very nature of atoms themselves, is not a fixed rule but a variable preference that changes depending on where you are in the universe. The implications of this are so profound they are difficult to overstate. It would mean our corner of the cosmos is not a representative sample. The physics we have painstakingly unraveled would be merely local bylaws, not the cosmic constitution. There could be vast regions of space where atoms cannot form stable molecules, where stars cannot ignite, or where gravity operates with a different strength. The universe would be a patchwork of different physical realities, some barren and lifeless, others perhaps hosting forms of existence we cannot even conceive. This idea challenges not just our science but our place in the cosmos. We may live in a fortunate bubble where the numbers are just right for us, a tranquil oasis in a multiverse of chaotic and inhospitable physics. The search for absolute truth would have to confront a universe where the rules themselves are written in shifting sand. Even the vast cosmic web has its empty chambers. In the constellation of Boötes, there lies a sphere of near-nothingness so immense it defies easy comprehension. This is the Boötes Void, a region of space roughly 330 million light-years across that is almost completely devoid of galaxies. To put that scale into perspective, if our Milky Way were placed at its center, the nearest edge of this void would be over 65 million light-years away in every direction. In a volume of space that should contain thousands of brilliant galaxies, astronomers have found only a few dozen, leaving a haunting, desolate bubble in the fabric of the cosmos. This is not a simple empty patch between filaments, it is a staggering cosmic desert, a vacuum on a scale that challenges our understanding of how the universe organized itself after the Big Bang. How could such an enormous region end up with so little? One leading theory suggests it is the result of a merger. In the early universe, smaller voids, the natural bubbles within the cosmic web, may have coalesced and joined together like soap bubbles combining to form one colossal empty chamber. Another, more exotic idea is that the Boötes Void is the imprint of an ancient pre-inflation flaw in the fabric of spacetime itself, a defect that was stretched to an unimaginable size during the universe's initial violent expansion, creating a permanent scar of emptiness. Then there is the theory of cosmic competition. In the denser regions of the early universe, matter was drawn toward the strongest gravitational pulls, robbing the future void of the raw materials needed to build galaxies and leaving it a barren wasteland. Whatever its origin, the Boötes Void is not unique. Other giant voids have been discovered, each a testament to the universe's lumpy, unpredictable architecture. These structures are far from inert, however. The sheer emptiness of a void creates a gravitational repulsion, gently pushing the surrounding galaxy clusters away from its center. This reveals that nothingness itself is a dynamic force, shaping the motion of galaxies on the largest scales. The existence of the Boötes Void forces us to confront a humbling reality. Our own Milky Way resides in a relatively dense suburban cluster, but we are surrounded by these abyssal regions of nothing. The cosmic web is not just a map of where the galaxies are, but a chart of profound emptiness, a reminder that the universe is primarily a void, punctuated by rare, glittering islands of matter. A particle can arrive on the other side of a wall without ever having climbed over it. This is not science fiction, it is quantum tunneling, a daily reality for the subatomic world that completely defies our classical intuition. In our everyday experience, if you roll a ball up a hill without enough energy to reach the top, it will roll back down. It cannot spontaneously appear on the other side. For an electron or other quantum particle, the rules are different. these entities do not behave like tiny billiard balls, but as smeared out waves of probability. When such a particle encounters a barrier, like an electrical force field it should not have the energy to cross, its probability wave does not abruptly end at the wall. Instead, it decays exponentially, fading but not vanishing, extending a ghostly tendril through the barrier and out the other side. There is a small but calculable probability that the particle will simply be found on the far side, as if it had passed through a phantom tunnel. It does not burrow or break the barrier, it literally cheats, skipping the impossible climb by leveraging the fundamental fuzzy uncertainty of the quantum realm. Without this bizarre effect, our universe would be dark and lifeless. Inside the core of our sun, protons need to collide and fuse to create helium and release energy. But they are all positively charged and they repel each other fiercely. The energy required to overcome this repulsion and push them close enough together is far greater than the energy the protons actually possess from the sun's immense heat. Classically, fusion should be impossible. Quantum tunneling provides the loophole. There is a tiny but non-zero probability that a proton will tunnel through the immense electrostatic barrier separating it from its neighbor. This happens constantly in vast numbers, allowing the sun to shine and power the entire solar system. Every photon of sunlight that warms your skin is a direct result of particles breaking the classical rules. This same principle is the bedrock of modern technology. The flash memory in your phone and computer relies on electrons tunneling through a thin, insulating barrier to store data as ones and zeros. The scanning tunneling microscope, which can image individual atoms, works by precisely controlling electron tunneling between a sharp tip and a surface. Our ability to see and manipulate the atomic world, and the very energy that sustains our planet, hinges on this one impossible-sounding quantum cheat code. The cosmic microwave background should be a random, featureless canvas, a perfect relic of a uniform beginning. Yet it holds a mysterious and controversial fingerprint, a pattern that seems to point a finger in one specific direction. Scientists have nicknamed this alignment the axis of evil, a name that reflects how deeply it disturbs our fundamental assumptions about the cosmos. The cosmological principle, a cornerstone of modern science, states that the universe is homogeneous and isotropic. This means it should look the same in every direction, with no special places and no preferred axis. The axis of evil directly challenges this. When researchers analyze the subtle temperature variations in the ancient afterglow of the Big Bang, they find that certain large-scale patterns, like the alignment of hot and cold spots, are not randomly scattered across the sky. Instead, they appear curiously coordinated, loosely aligned along a particular plane that slices through our solar system. It is as if the universe, in its first whisper, was imprinted with a subtle arrow, a directional bias that should not exist. The implications are staggering. This could mean that our universe is not the same in all directions on the largest scales. There might be a cosmic north and south, a fundamental lopsidedness to reality itself. One possibility is that this is a ghostly echo of something that happened before the Big Bang, a pre-existing structure or a gravitational wave from a prior cosmic epoch that imprinted its direction onto our newborn universe. Another, more unsettling idea is that we are seeing the drag of our universe moving through a larger multiverse, a structure that provides a background directionality we were never meant to see. Or perhaps most humbling of all, it could be a statistical fluke, a grand cosmic illusion seen only from our particular vantage point. But the anomaly has stubbornly persisted, even as we collect more precise data from powerful space telescopes. If it is real, the axis of evil forces a profound philosophical shift. We would have to abandon the comforting idea of a perfectly uniform cosmos and accept that the universe, from its very inception, had a preferred direction, a hidden spine around which all of creation is subtly organized. The universe might harbor a secret exit. Black holes famously devour everything that crosses their boundary, but the same mathematics that predicts them also allows for a perfect opposite, a white hole. Where a black hole's event horizon is a one-way door inward, a white hole's horizon would be a one-way door outward, a cosmic fountain from which matter and energy could only emerge, never to return. Nothing, not even light, could ever enter its domain. It would be the ultimate source, an uncrossable boundary that perpetually expels its contents into our universe. General relativity, Einstein's masterwork, treats these two objects as two sides of the same coin, mathematically symmetrical solutions to the equations governing gravity. One is a bottomless pit, the other is an unclimbable mountain. While we have overwhelming evidence for black holes, a confirmed white hole has never been observed, leading many to question if they are anything more than a fascinating mathematical ghost. Yet their theoretical possibility opens doors to extraordinary explanations for cosmic mysteries. Some physicists speculate that a white hole could be the other end of a black hole, connected by a theoretical bridge through space-time called a wormhole. In this view, the matter falling into a black hole in our universe might be violently ejected as a white hole in another universe entirely, or perhaps in a distant part of our own. This offers a tantalizing, though highly speculative, vision of a multiverse where our cosmos is connected to others through these cosmic plug holes. Another, even more profound idea is that the Big Bang itself was the ultimate white hole event, a singular, explosive emergence of all space, time, matter, and energy from a point of infinite density. This would mean our entire universe is the output of a primordial white hole, the grandest possible eruption from a source we can never look back into. For now, white holes remain in the realm of theoretical possibility, a stark reminder that the universe's strangest truths often begin as equations on a page, waiting for reality to catch up. Dark energy's relentless push could one day unravel the very fabric of reality. The universe is not just expanding, it is accelerating, and if this acceleration continues to intensify, it points toward a final, violent fate known as the Big Rip. This is not a slow drifting apart of galaxies, but a scenario where the force of dark energy becomes so overwhelmingly powerful that it overcomes every force that holds things together. First, the gravitational bonds tying together our local group of galaxies would be severed, sending our cosmic neighbors flying off into an ever-widening emptiness. Then the expansion would turn inward, targeting individual galaxies. The Milky Way itself would be torn asunder, its stars scattered like dust in a hurricane. The violence would escalate. As the stretching of space becomes infinite, our solar system would be ripped apart. The sun's gravity would no longer be able to hold the planets in their orbits. Earth would be flung into the isolating dark, but the end would not stop there. The force would then target the planet you stand on, overcoming the gravitational pull that makes it a sphere. Mountains, rocks, and the very ground beneath your feet would be shredded. Finally, in the last fleeting moments, the expansion would attack the building blocks of matter itself. The bonds between atoms would be snapped, nuclei would be torn from their electrons, every molecule, every atom in your body would be violently dissociated into a diffuse, non-interacting cloud of fundamental particles, forever isolated from everything else. The timeline for such an apocalyptic end depends entirely on the true nature of dark energy. If it is what physicists call phantom energy, a form that grows stronger over time, then the countdown has already begun. Current estimates suggest this ultimate dissolution could occur in as little as 22 billion years from now. While that is an almost unimaginable span, it is a finite one, a ticking clock on the cosmos itself. This stands in stark contrast to other proposed fates, like a slow heat death or a gradual fading. The Big Rip is an active, dramatic, and total destruction of structure at every level. It is a reminder that the same mysterious force responsible for creating the vast, majestic cosmos we see today might also be the very agent of its ultimate and absolute annihilation. We exist at a truly special moment in cosmic history, a brief window where we can still see the universe's deepest past. For most of human history, our view of the cosmos was limited to the few thousand stars visible to the naked eye. The grand scale of the universe, its birth and evolution, were complete mysteries. Telescopes changed everything, but even a century ago, we did not know other galaxies existed. We thought the Milky Way was the entire universe. Today, we have a front-row seat to cosmic history itself. Our most powerful observatories, like the James Webb Space Telescope, act as time machines, capturing light that has been traveling for over 13 billion years. We can watch galaxies forming in the early universe, see the first stars igniting, and trace the creation of the very elements that make up our bodies. This golden age of observation is not a permanent state of affairs. It is a fleeting opportunity. The universe's accelerating expansion, driven by dark energy, is creating a cosmic horizon. The light from the most distant galaxies is fighting a losing battle against the stretching of space. Their photons are being stretched into longer, redder wavelengths, their energy fading. One by one, these ancient galaxies will be carried beyond our view, their light stretched into invisibility. In the far future, astronomers on Earth, or whatever world harbors intelligence then, will look up at a much darker sky. The evidence of a grander cosmos, the cosmic microwave background, and the distant galactic superclusters will have vanished. Their universe will consist of only our local group of galaxies, a lonely island in an ever-expanding void of blackness. They will have no way of knowing that the universe began with a big bang, or that it was once filled with countless brilliant islands. All that evidence will be gone, carried away on the unstoppable river of expansion. We are uniquely privileged to live in this era of discovery, a time when we possess both the technological capability to see far and a universe still transparent enough to be seen. We are the first generation to map the cosmic web and the last that might ever see its full, glorious extent. This is our one chance to read the story of creation before the final pages fade away forever. The very act of looking at the universe might be what brings it into existence. This is the most mind-bending frontier in all of physics, a puzzle known as the measurement problem in quantum mechanics. In the subatomic world, particles do not have definite properties until we measure them. An electron exists in a blurry cloud of possible locations and states, a superposition of all potential realities. It is only at the moment of observation that this cloud of possibilities collapses into a single, concrete fact. Before you look, the electron is everywhere and nowhere. The instant your detector clicks, it chooses a single location to be. This is not a limitation of our technology, it is a fundamental feature of reality. The most famous illustration of this is Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead, linked to a random quantum event until someone opens the box to look. The act of observation itself seems to force the universe to make a decision. The dominant Copenhagen interpretation of quantum mechanics simply accepts this as a brute fact, a mysterious collapse with no deeper explanation. It draws a line between the quantum weirdness of the small and the classical certainty of the large, but it cannot say why observation causes the collapse. This leads to a staggering possibility that consciousness itself is the catalyst. The participatory universe theory, championed by physicist John Archibald Wheeler, takes this idea even further. He proposed that we live in a cosmos that only becomes real through the act of observation by conscious beings. The universe emerged from the Big Bang in a hazy, unrealized state of potential, and it required observers to look back in time through the act of measurement to solidify its history and properties. In this view, the universe bootstraps itself into reality, and we are not just passengers but essential participants in its creation. We are the universe becoming aware of itself. Other interpretations try to remove the observer. The many worlds theory says the wave function never collapses. Instead, the universe splits every time a quantum choice is made, creating a near-infinite tapestry of parallel realities where every possibility is realized. In one world, you are listening to this, and in another, you are not. De Broglie-Bohm pilot wave theory suggests that particles are guided by a hidden wave, giving them definite paths we simply cannot predict. But the core mystery remains. Does the moon exist when no one is looking? Our intuition screams yes, but the raw mathematics of quantum mechanics leaves the question disturbingly open. The role of consciousness in the cosmos is the final, and perhaps the most personal, of the universe's surprising truths. It forces us to ask if the mind is merely a byproduct of physical processes in the brain, or if it is something more fundamental, a feature of the cosmos as basic as space and time, woven into the very fabric of reality from the beginning. These truths reveal a universe far stranger and more magnificent than we ever dreamed. We are not living in a simple, predictable cosmos, but in a realm where time is personal, space is stretching, and reality itself may be a holographic projection. Our existence is a fleeting moment in a 13.8 billion-year saga, written in stardust and propelled by forces we cannot see. We have learned that we are made of atoms forged in long-dead stars, that we are orbiting a black hole we will never see, and that the empty space around us holds the ghostly echo of creation. These discoveries do not diminish us, they connect us. They humble us by revealing our tiny place in the cosmic web, yet they inspire us by showing that we are a way for the universe to understand its own astonishing nature. The next time you stand under a clear night sky, remember what you now know. That pinprick of light is a message from the distant past. The darkness between stars is not empty, but filled with the quantum fizz of potential and the invisible threads of dark matter. You are looking at a living, breathing, and deeply mysterious cosmos. We want to hear which of these truths reshaped your reality the most. Was it the phantom pull of the great attractor, the chilling possibility of the big rip, or the quantum magic that lets the sun shine? Let us know in the comments and tell us what cosmic mystery we should explore together next.